Hey, grade 11, so we're on to reaction stoichiometry now. So a little reminder, this is when you have chemical reactions and you are trying to determine amounts of substances. So for example, if this much of something reacts, how much will be produced, etc. So just back to basics, quick reminder, the way we set up a chemical reaction, we've got our reactants on the left, so everything on the left hand side we call a reactant, and everything on the right hand side, those are our products. Okay. Now, with stoichiometry, you need to remember all of the formula that we've seen so far. So you need to remember that N is equal to M over M. This is the main one. Then we've also got N is equal to V over Vm. This one is only for gas at STP. And then if we've got solutions, there's also C equals N over V, or C equals M over MV. Okay, these are for solutions. Okay, now the steps, the steps for doing a stoichiometric calculation are pretty much the same every time. So firstly, always, even if they give you the chemical reaction and they don't tell you that you need to balance it, you make sure that it's balanced, okay? Because sometimes they'll give you an unbalanced one and not tell you that it's unbalanced, and then everything just falls apart. Okay, so step one is to write a balanced chemical reaction equation. Okay, so let's say we've got A reacting with B to produce C. You would balance it. So in this case, I'm just going to use uppercase letters. So that's A, B, and C. Okay, so let's say those are numbers that we used to balance it. Step two, you convert all given info to moles. Okay, using these formulae. So depending on what you're given, you use these formulae to convert that information into moles. You have to convert to moles before you can do anything. Step three, okay, you use the balancing ratios to determine moles of what you want. Okay, so let's compare. Let's say we were told how much A we have and we want to know how much C will be produced. Okay, so remember this. I'm going to try and use the same language as I did last year. So what we have, okay, to what we want. So we will have been given the amount of A and we want the amount of C. So you write down the balancing numbers. That's A is to C. And you take the value of A. So in A, you'll have a number. Okay, you'll actually have a number for this, and this is what you're going to be looking for. So you'll take your number for A, you'll divide it by its balancing number, multiply that by the thing you want's balancing number, and that will give you the amount of C. Okay, and then you need to actually write out for me what you've done. So you'd say number of moles of C equals number of moles of A divided by A times by C. Okay, so you must write that statement for me. It is worth a mark. And then step four is you then convert the moles of what you want into whatever they ask for. So if they ask for mass, you then have to use this formula to go from moles to mass. If they want volume and it's a gas at STP, you'll use this formula. If they want volume and it's a solution, you'll use one of these formulae. Okay. So you convert the moles of what you want into whatever the physical property is that they want you to give of what you want. So this could be mass, it could be volume, it could be concentration, etc. Okay, using these formulae. Okay, and that's all there is to it every single time. So I'm going to erase these steps. Please make sure you write them down. I'm going to erase them. We're going to do two examples, one easier one and then one slightly trickier one. And then you guys are going to practice this second. Pause. Okay guys, so here's our question. We are going to consider the reaction of 5 grams of hydrogen gas as shown below. So we've got hydrogen and oxygen gas reacting to form water. And the first question is to determine the mass of oxygen gas that will react. So we know that we've got 5 grams of hydrogen gas reacting. Let's write that. We've got 5 grams of H2 gas reacting. And we want to know the mass of oxygen gas that's going to react. Now the first thing you do is make sure you have a balanced reaction equation. Okay, so let's check. We've got 2 hydrogen atoms there, 2 hydrogen atoms there, that's cool. 2 oxygen atoms here and only 1 there. Okay, so that means we need to put a 2 over there. That balances my oxygens, but now that throws my hydrogens out. So I've got 4 hydrogens on the right, I need 4 on the left, so I'm going to put a 2 over there. Okay, so that is now balanced. Now we need to determine the mass of oxygen gas that will react. Remember our steps. Step 1, we've just done. Make sure you've got a balanced reaction equation. Step 2, convert what you know into moles. So this 5 here, this is not moles, this is mass. This is 5 grams. So we've got to convert that into moles. So we must write down all our formulae, and please use subscripts now because we're dealing with more than one compound. So use a subscript to indicate to me which compound you're currently busy with. So the number of moles of H2 will be equal to the mass of H2 over the molar mass of H2. Okay, that's equal to 5 over the molar mass of H2 is 2 times the molar mass of one hydrogen atom, which is 2. So that means we're going to have 2,5 moles of H2 gas. Okay, so that's step 2 done. Step 3, this is where things get a little bit trickier, is to convert what we have to what we want by using the ratios from our balanced equation. So just a reminder, if there's no number here, it means that that's actually a 1. Okay, now we have H2, we want O2. So H2 to O2. H2 number of moles is 2,5 to the number of moles of O2. And from our balanced reaction equation, that's a 2:1 ratio. Okay, so to determine the number of moles of O2, we take the number of moles of H2, divide that by 2, and then multiply that by 1, and that will give us the number of moles of O2. So the number of moles of O2 are equal to the number of moles of H2 divided by 2 times by 1. So that's 2,5 divided by 2 times 1, which is 1,25, I think. Yeah. Okay, so we've got the number of moles of O2 is 1,25. So that's step 3 done, and then the last step is to take the moles of what you want and convert that into what they want. They didn't ask for moles of oxygen gas, they asked for mass of oxygen gas. So now we have to go and do one more little sum. The moles of oxygen gas will equal the mass of oxygen gas over its molar mass. We know the moles is 1,25. We want the mass. And the molar mass is going to be twice the molar mass of one atom of oxygen, which is 16. Okay, so we're going to have 1,25 times 32. And we get 40. So the mass of O2 produced is 40 grams. Okay, and I want you to set it out like this, please. You obviously don't have to go to the right and then down. You can put everything under each other if you want to, if it's a bit more neat for you, but I was just going to run out of space there. Okay, so there are 3 calculations here. There's your calculation converting from moles of what you had to, from mass of what you had to moles, then moles of what you had to moles of what you want, and then moles of what you want to mass of what you want. Okay, so 3 little calculations here. So I'm actually going to erase this to do the second question because I'm completely out of space, except for this over here. I'm going to leave this because we're going to need that in the second question anyway. Okay, so yeah, pause it, quickly copy it down because it's about to disappear. Okay guys, so we did in the previous question, we worked out that the moles of hydrogen gas, these 5 grams of hydrogen gas, is the same thing as 2.5 moles. So I'm just going to write that there underneath my equation again. Yeah, okay, so we've got that 2.5 moles. Now question B is to determine the volume of water produced if the reaction occurs at STP. So we're interested now in water, and we want to know the volume of water produced. And they tell us that we've got a reaction at STP, but they don't tell us that it's a gas. So now we've got to think, can we use the gas at STP formula? We need to know that it's a gas at STP in order to use that. But look here, they've given us the state of matter. It is a gas at STP. So I'm just going to write here immediately that I can use this formula. Okay, I might not need to, but I know I can use it because it's a gas at STP. Okay, so step 1 is to make sure we have a balanced reaction equation. We do. Step 2 is to convert the given information into moles. We already did that in question A. Okay, so we can go straight to step 3, which is to determine the number of moles of the thing we want. So we want H2O. So we're going to write our little ratio thingies. So we've got H2 to H2O. Okay, I know H2 is 2,5. I want the moles of H2O, and we know from our balanced reaction equation that the ratio is 2 is to 2. So we're going to say 2 is to 2. Now to actually determine the number of moles of H2O, okay, we take the number of moles of H2, we divide that by 2, and then we times it by 2 again. So that actually means we're dividing by 2 and then timesing by 2, so we're cancelling it out. So basically the number of moles of H2O is equal to the number of moles of H2, which is equal to 2,5. Please do, just like in the previous question, please do show me this logic. Okay, you need to tell me that you understand that the moles are equal. You haven't just accidentally used the previous moles. You understand that it's the same value, which is why you are now using that value. Okay. So we've done step 3. Step 4 is to convert the information that we've just worked out, to convert the moles of what we want to whatever they want. So they want the volume of water produced at STP, so we can now use this formula. Okay, so we can say the moles of H2O is equal to the volume of H2O over molar volume. Now we know that that's 2,5. We're looking for the volume of H2O, and we know molar volume is 22,4. So we're going to go, 2.5 times 22,4, and we get that the volume of H2O produced at STP is 56 dm cubed. Okay. So that's the first example. Little bit, I want to say it's easier simply because the reaction we were dealing with was easy. But the maths is the same every time. Okay, it doesn't get more tricky than this. Not yet. When we get to limiting reagents, it'll get a little bit trickier. But for now, this is actually as tricky as it can get. I do want to do one more though, where the reaction itself is a little bit more, a little bit more involved. Okay guys, so here's our example 2. We have to consider the complete combustion of 5 deciliters cubed of propane at STP. Okay, so there's a little bit of trickiness here. Firstly, propane, this is an organic molecule. You will learn next year how to go from the names of organic molecules to their chemical formulae. Sorry, there's a cat on my computer. Okay, so I'm just going to tell you what it is now. Propane has the chemical formula C3H8. And this you do know, we did go through it last year. Complete combustion, when you're talking about the combustion of things, we mean we're burning it. Basically, we're reacting it with oxygen gas. Things need oxygen gas present in order to combust. So this basically means that O2 is our other reactant here. So question A, to write a balanced reaction equation, I've basically already given us everything we need here. So we're going O2 plus C3H8, and when we combust, we always have water and carbon dioxide as products. Okay, I'm going to just move that plus a little bit closer there. So notice I've left spaces in front of everything because we don't just need to write the reaction, we have to now also balance it. Okay, so let's start with the carbons. Okay, you always want to start with something where it only exists in one compound on each side. So carbon is only in one of our reactants and only in one of our products. So here we've got 3 carbons, which means we need 3 carbons there. Okay. Next, let's do the hydrogens, because they're also only in one compound on each side. So I've got 8 hydrogens there and 2 here, which means I must put a 4 there to balance out the hydrogens. And last off, we can do the oxygens. I've got 6 oxygens here, okay, 3 O2s, which is 6, and then 4 oxygens here. So I've got a total of 10 oxygens on the right. On the left, I've only got 2, so I'm going to chuck a 5 over there. Now the oxygens are balanced. Mush, you need to go away, my sweet boy, I'm working. Okay, so done question A, we've written a balanced reaction equation. Okay, question B. We are going to determine the mass of water produced. Oh, oopsie, sorry, I've left something out of our equation. Oxygen gas, eh? And propane is also a gas, and our carbon dioxide will be a gas. Okay, so determine the mass of water produced. Let's go for it. Same steps as always. Step 1, balanced reaction equation. We've already done that. Step 2, take the information you are given and convert it into moles. So this is the information that we are given, that we have 5 decimeters cubed of propane. So this C3H8, we've got a volume of 5 decimeters cubed there. And they've also told us this is occurring at STP, and my propane is a gas. So we know, because the first thing we need to do now is to determine the moles of propane, right? And to do that, either we could use M over M, but we don't know the mass, we know the volume. But because it's a gas at STP, we can use volume of propane over molar volume. Okay, so let's go for it. So that's going to be 5 over 22,4. Oopsie. Okay, and we get 0,22. So the number of moles of propane are 0,22. Now guys, when you're getting values that are quite small like this, I'd suggest that you keep 4 or 5 decimal places until you get to the very end. So only round off to 2 decimals at the very end. Okay, so for now I'm going to call it 0,2232. Okay. Next up is the mole ratios. So we know about C3H8. Okay, we want to know about, what do we want? Water, H2O. Okay, so we're going to write down what we have. We've got that is 0,2232 is 2, the number of moles of H2O. And now from our balanced reaction equation, that is a 1:4 ratio. Okay, there's a 1 there and our 4 for H2O. So to determine the number of moles of H2O, we take the number of moles of propane, we divide it by 1, and then we times it by 4. Okay, please show me that step. Okay, now we can put in values. So that's 0,2232 over 1 times 4, and we get 0,8929. Okay, so see, we would get to 8, sorry, because of the rounding. Okay, now let's double check. They asked for mass, not for moles. So we've worked out the moles of water. They want mass of water, so one more little calculation to do. The moles of water would equal the mass of water over its molar mass, and now we sub in. That is 0,8928. The mass of water is what we're after. And the molar mass of water will be twice the molar mass of hydrogen plus the molar mass of oxygen. Okay, so we're going 0,8928 times 18. And we get that the mass of H2O produced will be 16,07 grams. Okay. So this 0,2232, I'm actually going to go ahead and write it. That volume is now no longer important. We would rather have moles. So that's 0,2232 moles. We know the moles of propane now. This is important. Okay, so I'm going to erase B because I need more space for C. So please do pause it and make sure you've got it all down. Okay guys, so the last one I've made slightly trickier. The maths is not trickier, just understanding the question is a little bit trickier. So question C is, if I have 40 grams of oxygen gas present, is it enough to combust all the propane? So our plan here needs to be, we've got to first figure out, we know how much propane we need to combust, okay? We know that the moles of propane we have that need to burn are 0,2232 moles. So using that, let's check what mass of O2 do we need. Okay, so let's do a normal stoichiometry question, figure out what mass of O2 do we need, and then compare that to what we have, and then we'll see if we have enough or not. Okay, do you understand what I'm saying? So we'll determine how much of O2 gas we need, and then compare that to the 40 grams that they say we have. Okay, so let's go for it. We know the moles of propane. Okay, let's go through our steps. This is a stoichiometry question. We're determining the mass of oxygen gas needed to completely combust our propane. So we've got a balanced chemical reaction equation. That's step 1 done. Step 2, we've got the moles of the information we have. So that's step 2 done. Step 3, we go and use the balanced equation number ratios to find the moles of what we want. So we have C3H8 and we want O2. This is 0,2232 and this is number of moles of O2. And then from our balanced reaction, it's a 5:1 ratio, okay? Or rather 1:5 because it's our propane and then our oxygen. So it's a 1:5 ratio. So to determine the number of moles of O2, we say number of moles of propane divided by 1 times 5. So it's number of moles of propane divided by 1 times 5, which is 0,2232 divided by 1 times 5, and we get 0.2232 times 5 is 1,116 moles of oxygen gas. So from the moles of oxygen gas, we can figure out what mass of oxygen gas we need. So we're going moles of O2 equals mass of O2 over molar mass of O2. We know that that's 1,116. We want this, and the molar mass of O2 is twice the molar mass of oxygen. So it's 1.116 times 32. And we get that the mass of oxygen required for this reaction to take place is 35,71. We have 40 grams, and we only need 35,71 grams. So we can say it's enough. We can say 35,71 is less than 40, therefore we have enough. Okay, so I'm hoping you guys saw what the plan was there, how we executed the plan. Instead of using this 40 grams, we were just doing a normal stoichiometry question, work out how much oxygen we actually needed, and then compare that to the 40 grams to see, okay, did we have enough or did we not? Okay, so I'm going to leave you there. I think that's enough of you guys watching me do it now. You guys are going to try, and let me know if you get stuck. Okay.